Thank you for the kind introduction and having me here at the wonderful conference. I've learned a lot throughout the conference. So today I will talk about the Miura operators as R-matrices. So as you can see in the title, I'm relating two different notions in the that appears in the study of algebra. So Miura operator is an object that appears in the free field realization of some kind of vertex algebras. I will explain what this is in the next slide. But the important point of this work is that it can be thought of as a kind of R-matrix of some quantum algebra. And we have seen what the R-matrices are in different talks of this conference. And another important point is that I'm not just stating the problem and the result purely mathematical way, but I'm embedding this problem into some certain physical setup called M-theory, which also appeared in the series of lectures by Andy, with some membranes. And I'm going to convince you how this setup, physical setup, can motivate you to expect this answer. So in that sense, this fits into the theme of this workshop, physical mathematics. So let me begin by introducing what Miura operators are. So Miura operator is an object that appears in the free field realization of the W algebra. It's called Miura transformation, the free field realization. So what is a Miura operator? It's the object that's called Ri there. Okay, so it's an Ri in the middle, which is a linear combination of the former differential operator dz and the GL1 hat current, the current of the GL1 hat vertex algebra, JIZ, with some coefficients, which doesn't matter too much for now. So what I mean by GL1 hat current, it means that it's a current that satisfies this OPE relation that on the right, JIZ, JJZ of W, whose singular part has this double pole at Z equals W with some coefficient. And you can see that there's a canonical delta IJ. That means that it's totally non-interacting. They don't talk to each other. And that's why this is free field realization. So this is simple enough. And I'm going to give you a definition of the algebra of type GLN using by embedding it into a tensor products of such free bosons. This way, a way is that you take n copies of Miura operators, which are denoted by R1, R2 from R to Rn, and they just take the products of them from right to left like that, and just expand in the decreasing orders of the differential operator dz. So obviously in the reading term, you will get dz to the power of n, but in the coefficients of the lower order terms, you will start to see something, some curves, u1 of z up to un of z. So obviously this derivative will act on J currents on the right, and the explicit expressions of the U currents will be some complicated combinations of J's and its derivatives. And in some basis, it is known that these currents satisfy the OP relations of the W and algebra. So what I want you to notice is that this structure, this Miura transformation is just better than just saying that there's a free field realization. Better than just saying there's an embedding to the tensor products of free bosons. Because let's say I want to increase the rank n by 1, then I would just bring one more copy of the Miura operator, Rn plus 1 to the left, and I will just take the product. Then I'll get the new currents U's up to Un plus 1. So it's constructive in that manner. So what this should remind you is the structure of the product of R matrices under the coproduct. So I think it appears in one of the talks yesterday. So under the coproduct operations, the R matrices behave becomes a product. And yeah, that's the algebraic structure that I want you to notice. I'm giving this slide as a motivation why we could expect the Miura operator Ri is an R matrix. The next clue is more explicit, I would say. there's something called Maurer-Akunkov R matrix. So in the previous slide, I have given you a construction of the W algebra type GLN, and the ordering of the products of the Miura operator shouldn't matter to construct the W algebra. By which I mean, if I change the ordering of the Miura operators in the product, they should produce you the isomorphic W and algebra. And what does the job is what is called the Maurer-Akunkov R matrix, which is valued in the tensor products of two copies of free bosons, 0, 1 hat. So the relation that it satisfies is that the products of two R matrices, the products of two Miura operators are the same, are equal to each other by up to conjugation of R MO. So this is yeah, they're the same up to the conjugation of R MO R matrix. And I cleverly chosen the notation for the Miura operator as Ri. So if I just substitute the Miura operator as Ri, then you can see that this relation seems like a kind of Yang-Baxter equation. But to say this is really a Yang-Baxter equation, you have to say which quantum group it is and which representation they are intertwining. So that's the subject of this talk. And although I started from this pre-field realization of the W algebra, in this talk I will actually talk about some Q deformation of the problem. And while I occasionally comment on the result of the original problem, and I will explain what the Q deformation is in the next slide. So in physical setup that I talked about, there's some M theory background that's playing a role here, and there's a choice of a complex two-dimensional space, which I call C, and this C can be chosen to be C square, C times C star, C star times C star, and depending on this choice, the involved algebra changes. So for the first two cases, there will be some kind of affine type of Yangians. For the last case, it's going to be the quantum toroidal algebra of GL1, which I denote by U, Q1, Q2, Q3, GL1 double hat. It's a double affinization of the enveloping algebra of GL1, and it's we have in yesterday we have seen the quantum affine algebra, but there's an additional affinization, so we have additional Q parameters. So yeah, so I should say the first two cases, which involves the affine Yangian, have been studied by Kevin Costello and David Gaiotto, from which my work was greatly motivated. And yeah, the new ingredient is the last column, right, last row of the M theory that involves the background C star times C star, giving rise to quantum toroidal algebra. Okay, before going into the physics setup, I wanted to make this single slide, which strips off all the physics ingredients, but only delivers the mathematics contents. Because this, the audience of this workshop is mainly math-based. So I hope I can deliver some mathematical contents from the beginning. So, but unfortunately, I have to assume some backgrounds, some knowledge on the quantum toroidal algebra itself. But it'll appear later. So if you don't know what I'm saying about what I'm talking about, then bear with me just for one slide. So for the quantum toroidal algebra, there are two types of representations. One type is called vector, and the other is called FOC. So there's some infinite dimensional vector space V and FC. C is some label, some orientation. So it's a choice from 1, 2, 3. So there are two types of representations. It's a well-known thing, and we think of the R matrix that's intertwined, that's in between these two modules. This is between these two representations. So one way to define this R matrix is that you take the universal R matrix of the quantum toroidal algebra, call it R, and just map it through low vector tensor low FOC, and that's an R matrix. An important point is that the universal R matrix, although its existence is known, at least in the basis that I want to express, this explicit expression in terms of generator is not known. But I don't want this fully generic expressions for the R matrix, but I only want this RC, which intertwines the two modules. So I can the statement is that I can solve the constraint that R matrix that's the RC satisfies recursively, and yeah, there's some explicit formula expression for this RC. And using this RC, we can construct the Miura transformation for what is called the q-deformed W algebra, not the W algebra itself, but some q-deformed version of it. So let's define the image of let's define QWN. So this will be some q-deformed version of the W algebra GLN type. As the image of a quantum algebra, first you map it through some n-1 times of the pole products. So it will map to the n factors of the quantum algebra. And you further map it through tensor products of n copies of the Fock representations. Here I chose the orientation to be all three. So they're all aligned to each other. So there will be some set of operators on the tensor products of the Fock spaces F3. So that image is called QWN. And for that QWN, you have this commutative diagram. That's the statement. So there's a cup product, and from each factor, from the left, you have a surjective map to QWN plus n prime. So you're factoring this into a sum of n. Yeah. I'm going to construct the generators of the QWN by using R matrices. Yeah. So that part is not. Yes. So I think it depends on what I define by T, right? Yeah. By the way, this is not how originally the q-deformed W algebra was defined by Frankel Reshatikin, because I was going to mention this in this slide. Sure. Right. But yeah, in Schiffer and Brasser, they didn't put it in this way. I mean, they for the affine Yangian, they show that the Miura map exists for the W algebra, but this is the q-deformed version of it. So that's the new thing. Okay, so where am I? So yeah, there's a commutative diagram, and there's an embedding from QWN plus n prime to the tensor product of two factors of QW induced by the coproduct, and this embedding is exactly realized by the factorizing the products of R matrices. That's the result. And moreover, so as I said, this is not how originally the q-deformed W algebra was realized, and it's actually defined by defining something called the screening currents and taking the common, what is called the commutants of the screening charges. And another statement is that even if you define this way, the QWN is going to be isomorphic. Okay, so I think this is the most important slide. So any questions so far? Not. I will start talking about physics. So this is an I-line. I'll explain how this problem is embedded into some physics setup involving M theory and the branes and the 5D Chern-Simons theory. So yeah, basically all the ingredients that you have seen, such as R matrices, are realized by some configurations of the branes in the M theory. So let me start by explaining what twisted M theory is, initiated by Kevin Costello. In this lecture, I think you have heard that the M theory is expected to be the UV completion of 11-dimensional supergravity. So it's certain 11-dimensional theory, and I can put it on any 11-dimensional wall volume. And I take this wall volume as simple as just R7 times C. And as I promised, there's a choice of a complex two-dimensional space, C, and that's exactly what I wrote C as C there. Okay, so on this space, I take the flat metric, and I'll implement what is called the omega background. So this is the reason why I split this R7 factors into R2, 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 and R. So what omega background means is that I want to turn on some potential that has to do with the rotations of the R2 factors. So I just lose some degrees of freedom, having high energy on with respect to these rotations. I just look at the locally near the origin, which is fixed points of these rotations. So physically, what that means is that I can choose certain supercharge Q, epsilon 1 and epsilon 2, where this epsilon 1 and epsilon 2 governs how high this potential it is, how large the potential well it is, such that Q squares to exactly the isometry of rotating the R2 planes. And if you want the detail, that's realized by some freeform background that exists in the 11-dimensional supergravity. So one important fact about this theory is that under the cohomology of this Q, the theory is topological along R7 and holomorphic along C. So that means that the theory doesn't depend on the metric of R7 part, and it only holomorphically depends on the C part. And moreover, I implemented the omega background with respect to the rotations. So the physics gets localized into the remaining 5-dimension, which is R times C. So it becomes a holomorphic topological non-commutative 5D Chern-Simons theory. So it's living on R times C. It's a Lagrangian theory. Its action is written right here. If you're familiar with the 3D Chern-Simons theory, you will recognize a similarity in this action. There's a crucial differences, which is that even though I have a Chern-Simons 3 form, I have to make the action 5 form. So this omega is used where this omega is the holomorphic 2 form in the complex plane. And also there's a non-commutativity in the complex space. So the product, the wedge products of the differential forms are deformed into Moyer products. So yeah, the definition of the Moyer products is written on the right. So yes. I'm sorry? True. So the constraint is that I'm keeping this Calabi-3 condition. So epsilon 3 is not independent. Right. That's why I said eventually the theory get localized to 5D, which is transverse to R2, R2, R2. Okay. So that's the twisted M theory and the 5D Chern-Simons theory that arises from it. And on top of this theory, I start to introduce membranes. So as you have heard, there are two kinds of branes in this M theory, which are M2 branes and M5 branes. M2 branes are 3-dimensional extended objects. So by some symmetry reason, in this setup, it can only wrap one of the R2 planes and the real line R. Whereas M5 branes are 6-dimensional objects, and by the symmetry reason, it can only wrap 2 of the R2 planes and a holomorphic curve inside the C complex 2-dimensional space. So here I label the choice of the complex curve inside C star times C star by P and Q. So C upper P and Q is nothing but the curve that looks like x to the Q z to the power minus P is constant. But most of the time, I will just restrict to the case where P comma Q is 1 comma 0 actually. If it's 1 comma 0, as you can see, it's z equals constant. So it's the x plane. It's supported on the x plane. Okay. So I tabulated some these choices of the M-branes, M2 and M5, in this table. So the goal of the point that I want to deliver here is that these M-branes, M2 and M5, have to be seen as some kind of defects in the 5D Chern-Simons theory that I introduced in the previous slide. So as I said, M2 branes wraps one of the R2 planes. So that's 0, 1, 2, 3, or 4, 5. But it also wraps the RT. So in the effective 5D Chern-Simons theory perspective, I don't see R2, R2, R2 factor. So I only see the defect object that's wrapping R direction. So in other words, any M2 brane gives rise to line defect in the 5D Chern-Simons theory. In the most generic case, I can bring L amount of the first kind, M amount of second kind, N amount of third kind. Their orientations are different in this R2 factors. So let's say I have L and N amount of them and just superpose one to the other on the RT direction, then I will have a line defect that's labeled by M and N, MN. So that's the line defect LMN. In the same way, if I have an M5 brane that's supported on two of the R2 planes, there are three choices. So M5001 means I don't fill in the third R2 factors. So it fills first two R2 factors and the C star X. If I 010, it means I don't fill in the second factor, so it fills first and third R2 factors. And the same for the 100. So in most generic case, I can bring LMN, capital M, LMN amount of them, and as a whole, it will give rise to they will give rise to a surface defect that I call S element. So these are some line and surface defects that can be constructed from the M theory point of view. Yes.
The superscript 1, 0 that is on X.
True. The superscript PQ in general is PQ. It's exactly the same as the choice of the C curve above. It could have been more general than PQ, but actually it will be always 1, 0. So just please forget about that superscript. The subscript is the support in the R2 directions. Which R2 plane I choose the sign 5 brane to wrap. Okay, so the point was that M2 brane gives rise to a line defect. M5 brane gives rise to surface defect. Actually, this brane setup is not unrelated to what Andy was talking about in the context of the class of series and surface defects. I will not go into that, but if you're interested, you can ask later. Are you asking what the 11-dimensional wall volume is?
No, but you start with the 11-dimensional. Then you can get now they set up the M theory is 11. Now set up the error on line defect and sub defect. I asked you about what is the origin of the line defect.
I see. So what I said is that in M theory, people believe there are some extended objects, which are called M2 and M5 branes, which were introduced in this lecture. M2s are 3-dimensional extended objects, and M5s are 6-dimensional extended objects. In this twisted M theory setup, I can't arbitrarily wrap this M2 and M5 in arbitrary submanifold because I want to preserve some symmetries. And these choices are restricted to be for M2. One of the R2 factors times R there, and for M5, 2 of the R2 factors and a holomorphic curve inside two-dimensional space, a complex two-dimensional space. And as you can see, once I localize to 5D Chern-Simons theory, you can see that M2 only leaves this R defect on the R direction, and M5 only leaves, this defects in the C star X direction. That's why it's line and surface defects. So for they are line and surface defects in holomorphic topological theory. And for general holomorphic topological theories, there are some algebraic structures that you can associate with. So I think this slide is even beyond the 5D Chern-Simons theory, but yeah, I'll always restrict to 5D Chern-Simons theory. If you have a defect which is topological, which means that, yeah, we have this line, and this line, the theory that doesn't depend on the metric. Then think of the space of local operators that lives on this line. So take two elements, then I'll say O1 and O2. So those red dots there. But as I said, it doesn't depend on the metric. So I'll just close this gap. I'll arbitrarily approach them, make them approach to each other. And eventually they'll just look like a single local operator. So what that means is that for a topological line defect, in the space of local operators supporting on this line, there's a natural product structure that's associated with it. So it defines an associative algebra by what is called the operator product expansion. And in the case of the holomorphic surface defect, the story complicates a bit because now I have a holomorphic dependence on the position. So take two local operators, O1 of Z and O2 of W, then I can also make them approach to each other by sending Z to W. But now I have to remember how this operation is singular, because it's not totally topological. And yeah, I have to assign at each level of poles what this product would look like. And this is exactly the OPE that appears in the vertex algebras. So holomorphic surface defect defines a vertex algebra. In my case, for the 5D Chern-Simons theory with line defects, we have seen there are line defects labeled by LMN, by the amount of M2 branes with different orientations. So I'll just name this associative algebra assigned to LMN to be M2 LMN. So M2 LMN is an algebra. In the same way, I'll call the vertex algebra, or actually, in general, it is expected to be quantum vertex algebra, but I will not go into that. I'll only take its mod algebra, which is associative algebra, and I will call this mod algebra of the car algebra to be M5 element for the surface defects. Okay. So for the 5D Chern-Simons theory, so we want to know how to classify, how to constrain these algebras. And for the 5D Chern-Simons theory, there's a nice statement that these algebras have to be always the image of some universal algebra, which I denoted by A, epsilon 1, epsilon 2. And it applies to any background. Remember, there was a choice of the whole complex two-dimensional space C. And for different C, it's going to be different algebra. As I show you in one of the slides, it could be affine Yangian type. In our case, where I chose this C to be C star times C star, it's going to be quantum toroidal algebra. Because the claim is that it has to be the quantum toroidal algebra. So what is a quantum toroidal algebra? I will give you the definition. I will give you a presentation later. But for now, you can think of it as certain q-deformation of the envelope, the quantum torus algebra generated by X and Z, satisfying that commutation relation on the right. So yeah, the name quantum toroidal algebra, I think it follows from the fact that it's a deformation of it. Okay, yeah, I'm going to explain why why we should expect such an answer.
Thinking about why it depends at all on what the speed is. And very nicely, I thought your definition of the line operator is something that the other dimension.
True. So this statement can be proven in the perturbation theory of the phi-d Jeong theorem, which means that you have to study some gauge invariance condition of the coupling of the line and surface defects using Feynman diagrams. And these Feynman rules, especially the propagators, can depend on this choice of background. So that's how the choice of the complex two-dimensional space enters. And I should also mention that the case of C star times C star that I'm going to talk about isn't established at the level of the phi-d Jeong theory, perturbation theory. All I'm giving you here is the expectation by consistency. All I'm giving you is that the answer should be the quantum fluid algebra by matching with some known facts about the algebra living on the M2 branes and M5 branes. But you know, in the phi-d Jeong theory, if I replace C by C star, there's a subtle issue of a boundary condition at the boundary. So C has one boundary, but C star has the boundary at 0 and infinity, and there's an issue of choosing that boundary condition, and that's exactly where.
Is it because you're not
So the algebra is non-commutative, yes.
But the transaminant itself is also not.
Yeah, yes. But I think imposing boundary condition imposing different boundary condition at the boundary of C and C star is more fundamental than just turning on the non-commutativity.
Yeah, but usually we think the local operators don't depend on the boundary. The local operator is far away from the boundary. But here's a little non-local, so maybe.
But I think and this question applies this to the same way there. Oh yes, true. That answers that at least. Sure. Okay. Yes. Yes. No. So that choice of support of the M5 brane doesn't have to do with the choice of Q1 and Q2. Yeah. Always Q1 and Q2 will be generic. Always. Okay. So for the line defects and surface defects, the statement will be like there will be low M2, low M5, then maps, surjectively maps this universal algebra to each algebras. Yeah, I'm going to talk about what they are. So yeah, as I said, this in principle, this statement should be studied at the level of the perturbation theory, the five-dimensional Simon's theory. Due to technical difficulty of having C star with different boundary conditions at 0 and infinity, I think there's no conceptual obstacle, but that due to technical difficulty, this hasn't been done yet. I have done the work in the case of the two-dimensional space C equals C2, C squared, where such a subtlety doesn't arise. But for this specific case where I have C equals C star times C star, yeah, it's things to be done. But I'm giving, again, I'll argue by consistency argument. Okay, so let me get into the line defects. So let me explain how we can determine what they are by using these techniques of the dualities in the string theory. Let me start from the coincident M2 branes. So in general, we have LMN amount of different orientations of M2 branes, but let's forget about other orientations, but having just think about having L00. There's certain operation that physicists do to reduce this M theory along one of the circle that you have in the 11-dimensional theory. As a result, you get some bound configuration of D2 and D6 branes. I think physicists this makes sense, and for mathematicians this doesn't make sense at all. But the point is that you by considering such configuration, you land on certain 3D n equals 4 theory that's engineered by such by studying open string spectrum of such D-brane configurations. And the problem of determining this algebra is it translates into studying the algebra holomorphic functions of X branch of this 3-dimensional n equals 4 theory. And this X branch, there's a way to read off what this X branch as a quiver variety, given the D-brane configurations. I think it also applied one of the talks. It is exactly the framed Jordan quiver, where the framing dimension is 1 and the dimension for the node is L. L was the number of the M2 branes. So you think this Higgs branch is nothing but Nakajima quiver variety, the Hilbert scheme of points. But in this case, there's a subtlety that I didn't explain. So this is not Nakajima quiver variety because this is not the simplest kind of 3D theory because of the existence of transverse circle. So there's a circle of the C star. And if this C star times C star was C2, then it would have been, this Higgs branch should have been Nakajima quiver variety. But because of the circle, so the open string have the winding modes, where the physicist say they're winding modes. So this Higgs branch gets uplifted to what's called the multiplicative quiver variety. This looks very, this is the defining equation for the multiplicative quiver variety. And it looks very similar to the Nakajima quiver variety. But yeah, as you can see in the equation, A, B, these matrices get a multiplicative uplifted. Yeah, so this is a certain variety, and we study the algebra of holomorphic functions in when the omega there's no omega deformation in the 3D theory. When we don't turn on the non-commutativity. And yeah, so this is some commutative algebra of holomorphic functions. And then because of the omega deformation, so you can think of it no. I'm talking about trigonometric. No, yeah. What quantizes the multiplicative quiver variety that I just showed you is, yeah, it's trigonometry. It is mentioned here. Yes, I was going to say yeah. So omega deformation, what it does is that even though you start with this 3D n equals 4 theory, you again, give some potential with respect to R2 rotations among this R3, eventually becomes a line one-dimensional theory. So because of the reason I explained, you define some non-commutative deformation of the algebra of functions. So the result is known from previous works to be the spherical Chern algebra, spherical Daha of type GLL. I could have given the definition. Okay. Yeah, so I could have given you the definition of Daha first and then spherical subalgebra and then McDonald representation. But let me just give you this as a definition. So just take these set of difference operators that's written as PMN. There are some formal variables xi's and some rational functions and some difference operator q1 to the power of dx. So q1 to the power of dx is exactly the thing that shifts x by q. These are some generators, and by these you generate some algebra. This is spherical Daha. Right. So what I'm trying to deliver is that the M2 L00, the M-brane algebra, in the case of coincident L amount of the M-branes, is the spherical Daha of type GLL. And in the particular case of L equals 1, if you only have one sheet of M-brane, it's nothing but the quantum toroidal prose algebra. Okay. So in this way, by using duality, we argue that we have determined the algebra that's living on the M2 branes. So now enters the quantum toroid algebra. So there's a mathematical fact that's known for the spherical Daha by the theorem of Schiff van der Wassero, or each L, non-negative L, there's a surjective homomorphism from quantum toroid algebra to the spherical Daha, M2L00. This happens at H level, each rank L, and in the large L, it approaches, it wants to be the quantum toroid algebra itself. So in that sense, it's the quantum toroid algebra is the large N limit of the spherical Daha. And moreover, one important fact is that the quantum toroid algebra is known to be trially invariant. It's not true for the spherical Daha itself. As you can see in the previous slide, you may remember that Q1 and Q2 parameters play different roles. Here and there, Q1 and Q2 parameters obviously play different roles. But in this map, the quantum toroid algebra is symmetric under the exchange of Q1, Q2, and Q3, but the projection is not invariant. So I'm saying the natural guess to be for this universal algebra is the quantum toroid algebra in this sense, because that was a statement. For the M2-brane algebra, you should have some universal algebra that surjectively maps to M2L00. So U, Q1, Q2, Q3, GL1 double hat is a nice candidate for this universal associative algebra. Now I'm giving you the definition of quantum toroid algebra. So this is complicated enough, but this is not so different from the quantum affine algebra that we have seen yesterday. All you have to remember from this slide is that the generators are called EK, FK, and H plus minus R. And they are gathered in this way into Lorentz series, formal Lorentz series, into currents EX, FX, and K plus minus X. There are some central elements, C and C perp. And their set of relations, complicated relations, that have to be satisfied by these currents. But all of these relations are governed by a single structure function G, and this structure function G is explicitly invariant under the exchange of Q parameters. So from yeah, by just looking at this, skimming through these equations, you can see that the definition is explicitly trially invariant. Okay, so in terms of these generators, the map that I introduced, the Chiffon-Bassero statement, is that can be expressed in this way. So EK generators map to these P1K difference operators, and so on and so forth. This map destroys the triality, even though quantum total algebra is triality invariant. Okay. As it should be, because I have chosen a preferred orientation of M2 branes when I say M2L00. Even though M theory background is invariant under the exchange of R2 planes, I have chosen which R2 plane M2 brane wraps, so the triality is broken. Okay, so there's some universal algebra, combinatorial algebra. We can do something more interesting in this 5D Chern-Simons setup. How about bringing two different types of two different line defects and superpose on top of each other? So on the left-hand side, this is called fusion by just this is a physical term. So bring L00 line defect here and L prime 00 line defect here, there, and then we want to bring them to each other, close to each other, and fuse. It will look like a single line defect, L plus L prime. What does it mean at the level of the local operators that's living on this wall volume? It should mean that I should be able to express the local operator that's lying on the fused line defect as an element of the tensor products of the left. So there's an embedding map from M2 L plus L prime, spherical Daha of type GL L plus L prime into the tensor products of two spherical Dahas. And I said each factor of M2 L00 receives surjective map from the quantum toroidal algebra. So there must be an algebra homomorphism from U to U, the tensor products of itself, delta, that makes this diagram commute. And as you may expect, this is nothing but the notion of coproduct for the quantum toroidal algebra. So by just realizing the quantum toroidal algebra in the framework of the 5D Chern-Simons theory, you would expect there's a co-algebra structure. Indeed, quantum toroidal algebra is equipped with a coproduct, and in terms of the generator, it looks like this. Maybe I should comment that in fact, quantum toroidal algebra can be equipped with infinite amount. So there are infinite choices of the coproducts, and this is what is called typically Dirichlet coproduct. I could have chosen the other, but let me not mention that other choices here. So what's the claim? So if you bring that coproduct and feed it here, then this diagram commutes for spherical Daha. Okay, maybe we can do something more interesting. So now let's bring let's get into the most generic case where you have L amount of M2 branes supported on the first R2, M amount of M2 branes supported on the second R2, and N amount of M2 branes on the third R2. The algebra that's supported on each stack of M2 branes will all be spherical Daha. But these spherical Dahas have Q parameters which play different roles. Each factor is a spherical Daha, but the role of the Q parameters permute. So they are different algebra in that sense, if you want to put them together. But what can you do? You fuse these three line defects into a single line defect using coproduct again. So yeah, feed coproduct twice and then map it through tensor products of M2 L00, M2 0M0, M2 00, and you get some math I define the image of this to be M2L0, sorry, M2LMN, which it is embedded in the tensor products of three spherical Dahas. We may call this the generalized McDonald representation of the quantum toroidal algebra, because we have seen a single factor of M2L00 realizes the McDonald representation of the quantum toroidal algebra. The explicit expression looks like this. It looks very complicated, but you recognize some pieces resemble the difference operator you find for the McDonald representation. But obviously now it's Q1, Q2, Q3 are more democratic in the sense that there are difference operators in Q1, Q2, and Q3, all of them. Any questions so far?
Can you ask you about
central element CNC perp. For the M2 branes, for spherical Daha, it was already the Schiffer and Basler map was defined in the sense in the way that CNC perp just maps to one, trivially map to one. So no matter and the coproduct formula just tells you that they just remains to be one. No. For M2, for spherical Daha and this more generalized McDonald, you wouldn't see more general values of C and C perp. I think so. So this should be realized as on the space of. I'm sorry. Maybe I haven't studied the reducibility. I don't see why it should be reducible now, but yeah. Okay, let's turn now into surface defects. I think I've. Okay. Well, if I can't reach to some points, then I will just omit it because I think, yeah, I can just deliver the contents that I can deliver. Yeah, we have done with the line defects, and let's get into the M5 branes giving surface defects. As I told you, it wraps two of the R2 factors in C star X plane. I will not explain, but because of some AGT type argument, one can argue that for single line for single M5 brane, the associated the algebra that's lying on this M5 brane is the free Q boson. So this is what deforms q-deforms the free boson algebra. As you can see on the right, there's a commutator of some modes AR and AS, and there's some powers of Q, and it's a Q deformation of the free boson algebra. Now, this free Q boson is also a surjective image of the quantum toroidal algebra. And the explicit map is written here. So EF K plus minus currents are mapped to certain complicated vertex operators, eta and C. They're here, and the phi's are here. So anyway, so they're expressed in terms of those modes AR in complicated manner. One thing you may note is that now C and C, the value of C is not 1, but C has to map to QC to the power of 1/2. So that's the one difference compared to the previous case. And yeah, maybe I didn't put emphasis on the orientation. So there's a choice of C, which can be 1, 2, or 3. And that's exactly how the M5 branes is oriented in the R2 times R2. Okay, so we have 3 Q bosons for single M5 branes. We can play the same game of fusing the defects. Now it's surface, not the line. So you just put them on together on top of each other. First, let's think about a coincident case. So they're precisely parallel to each other. So they're 0, 0, 1 type, all of them. And on the right, you're fusing into a single surface defect, 0, 0, n. So what you do is that you first feed n-1 times the coproduct and map each factor through the M5001 map. You'll find some image, something that's embedded into tensor products of free Q bosons. And I define that image to be M500n. This will be the q-deformed W algebra that's defined by Frank and Reshettikin and Shiraishi and others. I didn't explain why. You can, just as in the line defect case, you can do the general orientations of the M5 branes. So all I change in this slide is that the orientation of the M5 branes now are denoted by C1, C2 up to CL plus M plus N. As a result, you engineer the surface defect as LMN. You do exactly the same procedure, map it through L plus M plus N minus 1 times of coproduct, and then map each factor through the free Q boson. I'm defining some algebra that's embedded into tensor products of free Q bosons, and this image is defined to be M5 LMN. This is the q-deformed version of the Y. So there is something called Y algebra that generalizes the W algebra. And what I'm showing you here is the q-deformed Y algebra. So the Y algebra was constructed firstly by Gayode and Ropchak, and the free visualization was also studied by following studies of Miroslav Ropchak. And this is the Q deformation of it. Okay. So I think I have 2 minutes. So for the Miura operator now, I have to introduce the R-matrix. And yeah, you would ask how I engineer, how I put the R-matrix into the story. And this is a picture. Now I think of the intersection of surface and line defects. So here I'm bringing one M2 brane that's supported on 001 orientation, but the M5 brane is oriented in arbitrary ways. So C can be 1, 2, or 3. So they will make an intersection, and on the intersection there will be a local operator, which I denote by RC, supported at the intersection. Because I am forming this local operator from these two defects, it has to be valid in the tensor products of M2001 and M5C. So, and I want to constrain this object RC, or what's the condition that it has to satisfy. And in the 5D Chern-Simons theory, because it's a gauge theory, this configuration has to be, this intersecting configuration has to be gauge invariant. So you can study the gauge invariance condition. And the gauge variation receives contributions from this intersections of this small sphere around the intersection, the RC with the defects. So from the North Pole and South Pole, you get the contribution from the line defects. From the circle in the middle, you get the contribution from the surface defects. But this circle contribution is actually a linear combination. It can be decomposed into a sum of 2 contributions from inner and outer circles. So gathering all these contributions, you get this classical constraint for RC, which is the first equation in the bottom. So in principle, I have to study again. I have to draw some Feynman diagrams that computes this quantum corrections to this relation. But I didn't do this because of the technical difficulty, and I just argue by consistency argument that this equation in the first line has to be uplifted while respecting the algebraic structure. So it must be uplifted to the coproduct. So yeah, so this is a postulate. So the second equation says R delta equals delta op. Delta op is the opposite coproduct. Delta op RC. Now the point is that this is how mathematicians sometimes define the R matrix. So mathematicians we have the universal R matrix for the quantum toroidal algebra. It is an object that's valued in the tensor products of two quantum toroidal algebra, satisfying these three relations. But you can recognize the first equation is exactly the equation that I showed in the previous slide once I map to proper representations. And the point is that some facts are known about this universal R matrix. In particular, it has this factorized form where R is R bar K. K involves only the Cartan parts, and R bar has some expansion in degree. I have written the first two terms. But generic expressions in terms of these E and F generators are not available because of difficulty of which basis I'm expanding. So I can't directly use the known expression for the universal R matrix, but the point is that once I map to M2001 and M5C representation, I have this R matrix RC. I can just solve this constraint recursively, and yeah, I'm giving you the result. So yeah, RC is expressed as a product of RC bar times KC, and KC only involves the Cartan parts, and RC is expanded in degree, and it can be expressed as in terms of the vertex operators C. And note that it involves some difference operators. So now I'm getting back to the Miura operator story. Miura operator involved the differential operator for the W algebra, but we are talking about the q-deformed version of it. It should be uplifted to q-difference operator, and here's how the difference operator arises. In other words, the difference operator here is nothing but something that's provided from the M-brane algebra. So M-brane algebra was here is just the quantum torus because it's 001. That difference operator that realizes the quantum torus is what provides the difference operator for the Miura operator.
About the
I'm getting into that, but here for the purpose of the Miura operator, I'm just taking the simplest kind of M2, but arbitrary kind of M5. Yeah, it's one sheet of M2 and one sheet of M5, but M5 is arbitrarily oriented. But so yeah, for the case of R3, the answer actually simplifies. Actually, all the higher order terms just vanishes, and it just becomes a first order difference operator. Remember, the Miura operator for the W algebra was first order differential operator. So this is the uplift of it. Yeah, I really don't have time, so let me just explain that. This is the picture I view the factorization or R matrices. So you introduce M2 branes, passing through all of the M5 branes, and you fuse this surface defects, then this resulting R matrix will be factorized into the individual R matrices on the left, and that's the factorization. Yeah, so I think you asked about this T generator, and this can be one definition of T generator for the QW algebra or QY algebra. So just take the products of them, and then I just expand in the increasing orders of the difference operator, then it will be some T operator for QW algebra. Yeah, sorry. So I think I should stop, and I can't tell you why such a definition for QW algebra and QW algebra coincides with the one that's defined by Frank Reshettikin. That involves some study of realizing screening currents in this 5D Chern-Simons setup. And I just show you the picture that if you consider such a configuration where there's a finite length M2 brane stretched in between different sheets of M5 brane, that's exactly the screening currents. And using this fact, you can prove that these are the same QW algebra. And yeah, let me just stop here. Thank you.